Hi everyone. So right now I want to continue a little bit our discussion about intermolecular forces. In the previous video, I'll talk about the different types of intermolecular forces, and I compare at the very end the strength of each of these intermolecular forces. Now, when I compare that, I'm talking about those intermolecular forces as expressed in per mole quantity. So in other words, if I have 1 mole of hydrogen bonds, that's going to require more energy to break than 1 mole of a dipole-dipole interaction, and which will require more energy to break than 1 mole of London force interaction. However, when we're talking about the strength of these intermolecular forces in a molecule or a particle, there we might have different number of moles of the bonds. So for example, you might have a larger particle that exhibit various hydrogen bond possibilities and a smaller particle that also exhibits various hydrogen bond possibilities, because the larger particle has many more hydrogen bonds compared to the smaller particles. Then the hydrogen bond interactions in that larger particle would be categorized as stronger compared to the smaller particle, even though these are both hydrogen bond and therefore they should have had the same strength. Now, that would be true if we're uh, normalizing that strength to per mole basis. But if we're talking about a particle where there's different sizes there, then the ones that have clearly more hydrogen bonds would display a stronger interaction. So this goes to um, explaining why certain things that have only London forces, for example, might match another substance that displays hydrogen bond, because perhaps the substance that contains hydrogen bond is much smaller than the substance that displays the London forces. So as a result, when you take that size into account, then the two strength becomes flipped in terms of actual strength. But again, in per mole basis, the strength of those interactions are listed where hydrogen bond is the strongest, followed by dipole-dipole, followed by London force. So I want to give you an example here of how strong London forces could be. Remember that we said earlier London forces is the weakest of these interactions and it's barely there. However, if you have a really large molecule, London forces become substantial. Here's an example of a series of molecules that all display London forces. If we were to look at these molecules at room temperature, we find that the smallest of those molecules, a CH4 molecule, a hydrocarbon, exists as a gas phase. Now, clearly, if it exists as a gas phase, that means that the London forces in CH4 is just not strong enough to pull them together. The kinetic energy at room temperature overcomes the strength of the intermolecular forces. However, if you make that molecule large enough, still a hydrocarbon, but now you have 8 carbon and 18 hydrogens. This is actually octane, which is a component of gasoline. And as you know, gasoline is a liquid at room temperature. So at that point, there's enough London forces per molecule that it's strong enough to keep 2 octane molecules stuck together to overcome the kinetic energy at room temperature. If you increase the number of atoms to 20 for carbon and 42 for hydrogen, at that point you'll have a molecule that's we call a wax, which, as you know, is a solid, like a candle wax, for example. And again, at room temperature, there's enough London forces there to keep these molecules together to form a solid. Okay? So clearly here I want to illustrate that the size of the molecule plays an important role in how strong that force is going to be. Another point I want to make here is that why is hydrogen bond necessarily stronger than dipole-dipole? Because both hydrogen bond and dipole-dipole interactions are basically interactions between 2 dipoles, right? So why is it that hydrogen bond is categorized as a different type of force and it's a stronger one? Well, there's 2 reasons. Remember that the strength of any electrostatic interactions depend on 2 things. It depends on the size of those charges, and it also depends on the distance between those charges. So if we look at the first point there, hydrogen actually has a relatively low electronegativity. Because it has a relatively low electronegativity, that means the difference in electronegativity between, say, H and F is going to be more significant, or is going to be larger compared to the difference between electronegativity of carbon and fluorine. And what that means is, of course, this is going to be more partially positive compared to carbon if you're bonding to fluorine in this case. So what we're talking about there is that the charges themselves for a hydrogen bond is a larger value compared to a dipole-dipole. The second point is about the distance. So hydrogen is the smallest atom in the entire periodic table. Because it's small, it allows other molecules to come closer to it than if, for example, I have carbon there instead, because carbon is a much bigger atom. So because hydrogen is small, the r, which is the distance between one charge to the other charge, can be made smaller compared to when you have other atoms other than hydrogen. Okay, and that's the reason why hydrogen bond is stronger. The last point I want to make is in this video is just to talk about the fact that intermolecular forces is really important because it determines whether something is going to be a solid, liquid, or a gas, right? If you have a strong enough intermolecular force at a given pressure temperature, your substance is going to be a solid or a liquid. If it's not strong enough compared to the temperature-pressure combination, then it's going to be a gas. So as a result, it affects a few physical properties. Melting point, which is when, at what temperature the solid will convert to liquid. Boiling point, which is the temperature at which the liquid will convert to gas, as well as viscosity of the liquid, which is just how easily the liquid will flow out of a container. So for example, here I'm showing a picture of different viscosity fluids. This is the least viscous fluid. It just flows out very easily from the test tube. And as you can see, as you go further and further here, the liquid has a higher resistance to flow, which means it also has a higher viscosity. For something like this, like honey maybe, it really doesn't want to flow at all, whereas water flows very easily out of a test tube.